Okay, so let's do the lecture 1 part 3. These lectures are kind of chapters. Okay, so now so now we're gonna so we're done with the partial orders and the main tool, that is the Sohn's lemma, and so we're done with that part. And now we're gonna study partial orders with extra properties. Okay, so the first thing is we're going to talk about so as it turns out, first thing we're gonna talk about the some simple properties like what is joint and what's meet, and but as it turns out, we can capture a lot of things that you learn in undergraduate mathematics. That kind of the essence of it, we can capture um, in partial orders with like additional properties. So we're going to talk about like I'm going to talk about like topology, what is the kind of the essence of topology, and sigma algebra, Boolean algebras. Then we're going to talk about logics, and we're going to talk about geometry, which is a very important part. So yeah, so we're gonna the course is called it the lattice view. So you kind of start by looking at everything from the point of view of lattices, or like partial orders with additional properties. And I had to be very careful when I introduce these properties, and so I'll do this thing very carefully. Okay, and I'm following the textbook by Varadarajan. So that is the notations I'm using. Okay, now so the setup is let the definition let L be a partial order. Remember, to call this, when I whatever the thing that I write here, that act as less than or equal in your usual setting. So in Varadarajan, he uses this notation. Okay, so but the way we think about it, when I write a bracket and put that symbol there, whatever that goes in there act like less than or equal. Okay. uh, let's see. So the first definition is a definition of a null element. An element zero is called a null element. We have this property for all a in 0 is less than a. Okay. And it's kind of is an element that's at the bottom. So similarly, an element 1 L is called a unit element if for all a in L is less than. Okay. So let me yeah, so I use this. So it's like an element. Okay, so but these things should have to be the okay. So it's if 0 and 0 prime are null elements, then 0 is equal to 0 prime. In other words, the null element is unique. Remember, like we are not saying that any partial order has a null element. Okay? But this is only saying if it exists, then it's unique. In other words, if it exists, then unique. Okay. So proof. So if you have two elements, 0 and 0 prime, from star by star, you get, now 0 is a null element, and then the 0 prime is any element in the lattice. You can take a to be equal to 0 prime. So we get 0 greater than less than equal to 0 prime, and also similarly 0 prime is a null element, and then 0 is a element in L, so you can by star again you get 0 prime less than 0. So by these two you get 0 equals 0 prime. Okay. It might be confusing, but in the sense that it's not less than or equal. Okay, but it is. I'm using that notation. And this is the property of partial order. Okay, so let me give this exercise. So I have given, I've written down some more problems after the part 2. I wrote down problem 21 and 22. So this one would be 23. Show that if one and 1 prime are units of a partial order, then 1 equals 1 prime. Okay. In another word, the unit is also unique. When it exists, you can't have 2 units. Okay. Now, so we can so the definition, let F be a subset of a lattice, and I'm assuming that L is a lattice. Then let then there exists at most one element alpha in F such that is that for all for all A in F, alpha is less than A. And the second condition. So this is simply saying that alpha is a lower bound, and then the second one would say that it is the smallest one. If E if B such that B is less than A for all A in F, then B is actually less than alpha. Okay, and good. Notation. remember, like this is just the proposition, and once we prove the proposition, we'll get that there is at most one, meaning that might not have this element existing, or but if it exists, then there's only one. So when exist, we denote this by this notation. We denote this SIlva by this notation. Okay. Now, so let me write down the other statement. So we have element f in L, then there exists at least one element, let's call it beta in F, such that for all A in F, instead of this condition, we have A is less than beta. Okay. And if B is another upper bound, meaning if B is an element like this, then beta is less than okay. And when x is, this is denoted by okay. So these are called, and if f is just two elements, A and B, then we write if you're dealing with only two elements, or like n elements, then we write this A is in F. We write this thing as A1, A2, dot, dot, dot. And similarly, we write this. Now, so let's prove this thing. So this is, what we're doing here, for example, these are like the generalizations of supremum and infimum. Okay. And for example, like if L is the rational numbers, and example, you have the situation where can talk about this thing, but the supremum won't exist. And similarly, sometimes the infimum won't exist. I mean, sometimes supremum won't exist. Okay, so this is the generalization of that, and also the maximum. Okay, like if you have two numbers, this is the maximum of the two numbers and the minimum of two numbers. Let me, before proving this, so the thing that we need to show that the uniqueness is the thing to prove, because the rest of it is just a definition. Okay, and let me give out some exercises. And let me prove that. Let me prove the uniqueness. Let's finish with this. So assume let alpha wait. This element doesn't have to be in F. Okay, so this alpha doesn't have to be in the set that you started with. Like you can have a supremum that's not in the set. Okay, so let alpha and alpha prime in L that satisfy these conditions 1 and 2. Okay, you have two of these guys, and then it's the same as before, because if you take alpha and you apply the condition 2 for alpha, but you notice that alpha prime would set, you can take alpha prime to be equal to b. Okay, because alpha prime satisfies that condition, so you will get alpha prime less than alpha by taking b equals alpha prime into. Okay. And similarly, you can get alpha is less than alpha prime. Okay, so this will tell you that alpha is equal to alpha. Okay, so if it exists, then it is unique. Okay, now I leave the other side as exercise 24. Prove the proposition for this other one. It's again like a couple of lines. We call this thing 23 part A. We call this thing 23 part B. Okay, it's very trivial. Now, so exercise 24. let's do these exercises. So basically, the kind of the right thing to do is to go and look at the examples of that partial orders we had. But let me write this thing down, okay? I want you to kind of notice this. So when L, this is simply, let's say, real numbers under less than or equal, okay? For A and B, in here, A join B is actually minimum. So, and you can prove this thing, okay? Show that. For A and B in L is equal to this. And similarly, we have in general, is equal to the infimum. Okay. So infimum of this set. The thing that I want you to notice is we have the definition of this and this independent of the particular lattice that we're dealing with. Okay, so in different cases, we will get different answers. Okay, and similarly, you have the supremum for the other one, max and the sup. Okay, and let's do part B. We have a vector space. Let's do the set one. Let X be a set. And you consider L is equal to the power set of X and under the inclusion. Show that A which B is equal to A intersection B. And let's say wedge, so capital A in F. A, this is the intersection of this set.
Okay, but I just one of your little toothbrushes downstairs, so let me go grab that one. That was.
And similarly, the other one is the union. Okay. it takes some time and prove this thing because you have seen that because if you're working with a particular lattice, it's very uh, it's very common to common to define this joint and meet by kind of the operation that's inside your lattice, particular lattice. Okay, and let's do this one. Let V be a vector space and L of V be the linear, the set of linear subspaces of set of linear subspaces. V. And we have shown that LV with this one is a partial order. I mean, L of V is a bad notation, but it's okay. Write it clearly. Recall that. Is partial order. So find we have two subspaces A and B. What is A which B? What is A union B? Or like A B B, and this one. Okay, and now I'm reiterating go through these things, and also like I'm calling this course functional analysis, and we'll get there, and after the lecture one. No, after a while, not after lecture one. And the main object for our study is this guy, subspaces of a vector space V, and but on the other hand, the Boolean algebras comes into play as a small as a kind of a basic case. So second looks like that. It's like the videos and sharing what I was writing. Let me double check on the video and I'll be back. Okay, so let's get back to the lecture. It's good that I went and like looked at it, and as it turns out, if I'm not having the in focus, then you don't see it in the video. Okay, so I have to click the window. Anyway, so let me recall where we are at. So we have we're basically trying to define these two things. Have so we have this guy join and this guy called the meat. Okay, and it will be really interesting if I did it wrong. Let's see. Yes, exactly. Okay. So so this is the join, and that's the meat. Okay, and we don't use these words, so but I mean the thing is like I am really not doing the lattice theory, and anyway, like I mean you always work in a particular example. For example, would be in the world of sets, then I use intersections and unions and so on. Okay, so what we have, but I was defining things, but I was doing it a little carefully. So we are still working inside the lattice, not a lattice, not a lattice. Still working inside the partial order, and then I define what the joint and meat of a collection of elements is. But I'm not claiming that those things exist all the time. Okay, so and then I define the null element and the unit element, and then this is for a join and the meat, meat and the join. Okay, so the one that looks like the intersection is the meat. Okay, I put some easy facts, but when I gave a bunch of exercises, the point of these exercises is just to convince you that you can show these things. Okay, so these are not definitions. Okay, so this is saying that the meat, this gadget, is the minimum and so on in different partial orders. Okay. Now, and I mean, these exercises are easy, but the point is that it's show that. Okay, and again, find. So that means you have to find this thing and then show that it is the case. Okay, and there is something to prove. This is not trivial, and these things I don't have it in the, like, if you go back couple minutes, I've been talking about these things without nothing writing on the iPad, but you'll figure it out. Okay, so I won't redo that part. So let me move on. So let's do this thing. So we have we have a lattice, and you can like kind of turn the whole thing upside down. The things that are in the top goes into the bottom. So that's called the dual lattice. So let me write this thing down. Definition. let L be a poset. Consider. So I know that I just used the word lattice, but I haven't even defined what a lattice is. Okay. Consider this one. Call it like that. Kind of little tilt. Okay. Given by, so this it is the same L, and A, B, this is if and only B is less than or equal to A. Okay. For all A, B null, we have this. So you're flipping things, okay? So you can show that easily. Let's call it exercise 25. Part A, show that this is a partial loaded set, P poset. And it's fun to show that the supremums and infimums are switched. Let F be a subset of L. If let's say if union A in F A exists in here, then this thing in L exists, and let me call this element B exists, and this thing is equal to okay. So the kind of the joints turns into meets, and meets turns into joints. So there is a another statement. See, they don't have to know which one it is if I do it that way. State and prove the statement for this one. Okay. Now, so here are some examples. So there you can have like a lot of simple examples like this. This is A, B, C, D, and you have a partial order that looks like this. Okay, so in other words, the set L is 4 points A, B, C, D, and we have this thing the ordering. Ordering is a relation. Relation is a subset of the product set. So I can just specify these things by telling A, comma C, and A, comma D, and B, comma C, and B, comma D. Okay. And that's a way to specify the partial order. And what is A, B, B, C, C, and D, D. Okay, so you have those things too, because it has to be reflexive. Yeah, but the picture is like C is bigger than or equal to A, and so on. Now, in here, if you look at the set F to be A and B, you don't have the join of this set F, because join is the supremum. So we have this, because this one is a supremum and this one is a, I mean, both these things are upper bound, and but they're not comparable, so you cannot find the least one. Okay, and similarly, if you take these two elements, and then you cannot find a minimum. Take G to be CD. Then supremum. So this thing and does not exist. Okay, so in general, these things don't exist. Okay, and now so let's do this thing. So associated. So if we have A, B, C in here, we want to know that if this thing holds. Okay, and uh, we know that you can have a situation where you can't even like start talking about this thing, because you probably can come up with the example where one side exists and the other side doesn't even exist. Okay, So we call it exercise 26. Find 1, 2, 3, 4 examples where one side of 1, 2 exist, but the other side doesn't. Okay. So I mean, we had 4 examples. You want the first identity associated law, and then you find example where left side is exist and the other side doesn't exist. So there's no point in even talking about these things. Okay. Now, but another question is so proposition. If left hand side and right hand side are well defined, meaning that they exist. See, like a well-defined kind of include that it exists because I'm writing B join C, for example, in here, and then I'm writing that on this side. Like that means this has to exist as an element. Talking about the other thing. Okay, well-defined and exist. Then 1 and 2 holds. Okay, so this is so if these things are if they exist, then they're equal. Okay, so let me prove this thing. I think so. So let alpha be this guy. Okay. And let's say beta is this thing. So let's prove that let's prove that alpha is less than alpha is less than beta. I mean the less than means less than equal. Okay. So let me let's keep it like this because you're following Varadarajan book. Let's prove this thing. So so you can so alpha is equal to this, and alpha is greater than a, and alpha is Okay, because alpha is the, let me call it union. Okay. I'm calling it union, but I'm calling it union, but it should really be called join. Okay. So we have this, and because the alpha is the union of these two things, and so from this you get again okay. So this means so now from this and this, so we have A less than alpha and B less than alpha. And then you look at A union B. So A union B is the smallest upper bound, and alpha is upper bound. So for both these, so we have this. Okay. And now I can take A union B less than alpha and C less than alpha. And from the same argument, you get A and B union C less than alpha. Okay. But this is beta. So beta less than alpha. So it's okay. It's close enough. Okay. So we wanted to prove that, wanted to prove this, but we ended up proving this. Okay. And you can similarly, you can prove the other one. Okay. Start with beta and then you unpack and then you go from there. Okay. Similarly, alpha is less than beta. But from these two, you get alpha equals beta. Right, so the associativity holds when these things are defined. Okay, now let me leave the other one as exercise. So exercise 27, not 26. Sorry, exercise 26. Party show the version for this guy. Version for the intersection. Okay, and you meaning state and prove it. And then, okay, so here is something else. We didn't prove the commutativity. So show that. A, this is same as B. A. Okay. And you don't have to prove it because it's actually built into here. It's built into here, okay? Yeah. it boils down to this. If you actually want to prove the commutativity, we should be starting with not just a set F, should be starting with the ordered set. Okay, so just the fact that we are defining this thing in terms of F for a set F, because the elements in the set doesn't have order. So boils down to that. Okay, so you have the what I'm trying to say is very trivial. Okay. But you can like write some things. But if you want to actually really really want to do something with commutativity, you better start with the not a set F, but ordered set F. Okay? So the first element, second element, and then second element, first element. Okay. Let's prove this. Sure. So the associativity. Show this thing. If F1, F2, let me write this way. Formulate and prove. F1, F2, and F3 are subsets of L. Then so this is kind of a nice associativity law. Okay. So, but formulate it properly, okay? So something like this should work, but for example, the thing would be the key thing is I think it'll be easy to show that if all these things exist, okay, then they're equal. But see if you can show that if these things exist, everything in these two lines exist, then we automatically get that this guy is exist and it's equal to this. Okay. And so when you write, when I say it's formulate, yeah, very kind of think about that too. Okay. Okay. Now, so the associativity law, we were able to actually work with the case of partial orders, and when things exist, then it's all good. Okay. Now, this is the, now we are getting into the uh, the really serious topic. Mhm. This is the distributive properties. So the we call, say, is distributive. Let me not define things yet. So call the distributive properties. So these are the distributive properties. Uh, okay. Now, so two examples. So let's go through main three examples. Let's go over. Three examples. The first one is, let's say, real numbers get less than or equal. See if it holds. Okay. And the next one is power set of x. We call this thing 27. Power set of x with the inclusion. And this one works. Okay, because and this is we know that with intersection and union, this thing works. Okay, now the third example, so V is a vector space. And L of V is the collection of subspaces, set of subspaces. And then we consider L of V together with inclusion. Okay. And this, so this one is not distributed. So this is the big problem. Oh, not problem, but this is the kind of the dividing point of actually classical and quantum mechanics. We'll get there. So this is equation 1 and 2. So for example, so you take V to be R3. This is your V. And what is R2? 2. And so A is the x-axis and B is the y-axis, because both these things are subspaces. And let's take C is the set where x equals y, which is also a subspace. Okay, now in this case, if you compute A, V, B, C, this is equal to A, V. We take the intersection with the B and C, you will get zero space. And so this will give you A. Okay. But on the other hand, if we take A, V, E, so I think we proved that in this lattice vector spaces, this supremum is actually the addition of the subspaces. Okay, and that would be, in this case, you get R2, right? And also A, B, C is also going to be R2, right? So that means if you take A, B, B intersection A, B, C, that's going to be R2. So these two things are not the same. This is not equal to this. Okay, so that means the distributive property doesn't hold. Okay. So, but then you have this property. There is something, there is a weaker version of a distributive property. It's called the modular property. Modular property tells you if A less than C, so if C less than A, so A less than C, then we have A okay, and so exercise 28. show this for this guy. This lattice. So the point is like this lattice is, sorry, I'm using the, okay, I'll define lattice next. So the this property is the distributive property is not true for this partial order, but it has this modular property. Okay, and you can easily see that the partial order is distributive, then you have the modular property, because this is basically telling you that so if you look at this and this, if A is less than C, then this is C. This is A. So the modularity. It's C less than A. Okay, so that's the correct step. That's the correct step. This is C less than A. Okay, if the distributive property holds, then this is equal to A intersection B union A intersection C, and the A intersection C is equal to C. Okay, but the but this property holds for the subspaces of a vector space. Okay, and of course this holds for modules. Now, so let's move on. I'm basically describing a whole bunch of properties for the partial orders, and then I'll go back and study these things more carefully. Okay. Now, so here is the reason that I haven't been defining the lattice. So the next define this thing, directed sets. Oh, let me before this, let's just do this thing. Complements. So let L be a partial ordered set with 1 and 0. Okay. Let A be an element in L. An element, and A prime is called complement of L if A prime, this is 0, and A prime A is equal to 1. Okay. So again, the key examples is this one has complements. Has complements for has complements for any element. Okay. In this case, the complement is the set complement. So for A is a subset of X, then A prime is the set of simple X in X, such that X is not in A. And you can verify that these two properties holds. Okay. And in this case, it actually has this complement is actually unique. Can't have two. Okay. But let me contrast this with this setup. LV with this. So I mean, these are our two main examples. Okay. And so in this case, this for any W W as a complement. Okay, so let me give this in as exercise 28. Let's call it part 1 show. Prove that this works. And then it's actually if W is not equal to the V or this set, then W prime is and W then W W has more than one complement. Let's say V is over reals. Okay, so vector space is over the reals. You don't run into any funny business. So the picture is this. Idea is we take, let's say in the case of R2, we have, so this is your element, this is your subspace W, and then you can take W prime to be, let's say W is the x-axis, and you can take W prime to be the y-axis, And if you do that, then the intersection is the singleton, and also the sum is the whole space. So that means W prime is complement. But also you can take W prime to be y-axis. Okay. So the complement is not unique in this case. Okay. So in here, I'm asking you to prove that you can find more than one complement. So yeah, it's okay. You can. You had to probably play with the basis, and you take a basis for W, and then you extend that basis to the whole space, and then you play with that a little bit, and you'll be able to find two complements. Okay, but the idea is this, and let's show this one too. If L this thing is a poset, with 0 and 1, then 0 complement is 1 and 1 complement is 0. So what I'm trying to say here is I'm using this notation 0 complement 0 dash, that by writing it I'm saying that that's unique. Okay, you remember when I defined it, I said like this is an element called a complement and all that, right? This is because in general these things are not unique, but the null element and the unit has a unique complement, which is the unit and the null element. Okay, and that's why you have, I mean, in part B I removed the whole space and the singleton, and that's why. Okay, and good. And in general, later we will show that the Px is an example of a Boolean algebra, and so this is example of a Boolean algebra. We will show that for Boolean algebras the complements are unique. Okay, and so, okay, now finally I'll get to this directed sets. So basically I'm writing down a whole bunch of definitions, and I'll kind of dig into individual topics later. Okay, so here is a definition. Not definition, topic. Directed sets. So this is a really interesting one. So you remember sequences. You write it AN, but these things are actually proper formulation is, let's say this is complex sequence of complex numbers. So it's a function with the domain and a range. Okay, and this domain has the, I mean, in this case, this is a well-loaded set. Right, and we can even have like, what's the next element? What's the next element? That's all. right? But so the like limits, when you define limits, we have the notion of in integers, this we can go to infinity. That means this, like, we can go in the direction of infinity. And then once that happens, then you have the whatever the C complex numbers, they have a notion of getting closed. Okay. And so as it turns out, we don't need this set to be a well-loaded set to talk about limits. Okay, so the definition, a partial loaded set is called a directed set if for all A, B in L, there exists a C in L such that C is bigger than A and B. Okay, so doesn't matter where you are, you can always find a bigger element. A picture. So the partial orders, when I drew it earlier, they were like this, right? You have something like this. I'm sorry for the picture, but you have this is bigger than this, and so on, and this element is bigger than this one, and these two elements are not comparable, and so on, right? And the directed set, like with the integers are like this. It's like really nice, like a well-loaded set, right? And you can go up, you go infinity, right? And this directed set, it has the freedom, like in the case of partial loaded set, because we're not saying that it has to be a well loaded or even a total loaded set, but it has this property. So we can have all these weird stuff, but no matter where you are, we have two elements A and B here, A here and B here, and there is a C that's sitting above both A and B. Okay, so we can be like really messy, but we can always kind of go to like larger, like they have common larger elements. Okay, common upper bounds. I mean upper bounds. So this notion is, it tells you like this sort of direction, and this, as it turns out, this is enough to come up with the general version of a sequence. It's called a net, but the net is a function defined on a directed set. Okay, and then you talk about a function, you have the domain and the range, but for now we're interested in the domain. Okay, so we're not going to talk about nets for now, but we're interested in the thing that gives you direction. And the reason I'm doing this thing is we are not assuming that A the meet union of A B. Okay, we are not assuming that thing exists. It's terrible. not the join. Join is the one that's above, sits above. See, like we don't assume this. Okay. So, so the key example here, believe it or not, you have seen this thing. Okay. Key example. We have seen, yeah, you really have worked with the directed set, and we have actually computed this type of limits. And me give you the example, and you'll see. And I write down a bunch of problems too. Okay, so here is the example. So let A be an interval. In R, and you look at the let E be the collection of partitions of AB. So in other words, P consists of this x1, sorry, x0, x1, dot, 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 up to xn. That's a ordered pair where x0 is equal to A and xn equals to B, and we have x0 strictly less than x1, dot, dot, dot. So this is a partition, and show that, not that this thing is a directed set. Okay, and if you take two elements, and then you can look at the partition that you get by throwing in all the points on the union of those things, and that's another one. Okay, and so, and you have like upper sum and lower sum. Those are really functions defined on this collection of partitions. So given a function f defined on AP, let's say with values in R, and so we have U upper sum is a function from here into R. And for any given partition, you have this. So this is an example of a net. So you have a function that's defined on these things. Okay, and then you have the upper sums decrease. Okay, and then you have the lower sums increasing. And then you can talk about the limit and like when does this thing exist. Okay, and I will I'll go through this thing in the case of I'll do a little review on the Riemann Sturgis integral. I have do things like fx dx. This is the Riemann integration where you where the length of the intervals are done by this dx, which is the same as the length of the interval is the length of the interval. But you have something called FD alpha, where you have increasing function alpha, and then you kind of assign the distance to interval by using alpha. Okay, and it is pretty similar, but I'll go through this thing, define nets, and then prove the theorems, and we'll go through it in a later day. Okay, but I want you to notice that you think about this thing really, and when you did Riemann integration, we dealt with the taking limits of this particular directed set. Okay, now we define a lattice. A lattice. So again, in here there's lots of things. I'll have a little lecture on limits, and I will go over nets and how this directed sets. So this one, if you have seen the notion of a subbasis of a topological space, and what we're trying to capture here is what you call subbasis for a neighborhood basis. So the limits, when we introduce topology, we said like, okay, so we are doing topology because we want to talk about limits, and then I'm here and say like, yeah, there's no topology in here, and so yeah, so it's kind of topology get captured into this directed set structure. Okay, so we'll have whole discussion on how we go back and forth between topology and these partial orders. Okay, I mean that is the kind of the first theme of these lectures, the stone representation theorem. But we'll do weaker versions of it. Okay, so directed sets, and I'll have a whole lecture on this thing. Okay, and then I'll have a separate lecture on Riemann stages integral. So you can look at the Piazza and then you have the different topics. Now, let's go back. Finally, this is the lattice. So the lattice is a partial loaded set L is with unit and with the null element and the unit, and we write it nicely. Lattice is a partial loaded set with the following. First thing is 0 and 1 existing in L. And the second one is for any finite F, for any finite subset in here, these unions. So there's these guys. Finite meets and finite joints exist. Okay, so then the things become very easy to deal with. If this thing, these guys, exist for any F, then it is called a complete lattice. So if the joint and meet exist for arbitrary subsets, then we call it a complete lattice. If this thing and this thing exist for countable f, then it is, then we call this thing a sigma complete lattice. So the sigma stands for countable. Okay, sigma algebra, for example, has the countable unions and countable intersections. Okay. So it is an exercise. 28, 29. So I had the big list of partial orders, and I think all of them are lattices. Show that. All the partial orders we had are lattices. Okay, all the partial order, and then we had a huge list of them at the very beginning. It's in Piazza too. Yeah, these guys. Right here. Yeah. And I have a larger list in Piazza, okay? And I write this thing as a problem, but don't try to write a complete solution for this, okay? Just the most of them are trivial, but there might be one or two that's interesting. Okay, now I'm kind of so then I'm just trying to write a bunch of couple more definitions, and then kind of this would complete the introduction of the words, or like the definitions for the lattices. Okay, and then I'll go and then talk about limits next. Okay, so couple more. Let me add the page here. So I should have talked about this in here. So part C is in the next page. Okay, so you had exercise A, B, and C. C is in next page. So, so I mentioned that the Boolean algebras has unique complements, and so we have this definition. Let L the partial loaded set. The lattice. Let's assume the lattice condition from now on, because that means the join and meet exist for finite elements. An element A is in here is called a central element. If A has a unique complement. Okay. So the central elements are the elements with a unique complement. And for example, we will show that we have a Boolean algebra and all the elements would be central. And we will study something called if you just have the modular property, I'm not sure about this, but if you just have the modular property, if you look at the central elements of a modular lattice, and those elements would form a Boolean algebra. Okay, but we'll study those things, okay, later. But I just want to put down the definitions and then go from there. And I want to basically, I'm doing this thing because it looks like so far I did the Sohn's lemma and then some useless thing. I mean, it is useful, but it's not something you see in the normal curriculum. I want to go through these things and show that I'm up to something, trying to teach you a lot of I mean that this foundation is useful and can get a lot of things. Okay, so that's the point of this little discussion. That's why I'm just giving out names and not much theorems or propositions, but you'll go through those. So the definition, a lattice is called an irreducible lattice if uh, 0 and 1 are the only central elements of central elements of the lattice, because I didn't give a name. Okay. Now, here is the definition. And this one, you look at it and then you go like, kind of walk around for a couple of days. Geometry. Have is called geometry. Let me. and irreducible complemented modular lattice with finite rank. Is called a geometry. Finite rank means let me use the less than or equal to. Finite rank, the same thing as finite dimensions in the, that's a kind of the lattice version of the finite dimension. So finite rank means supremum over n such that all this exercise. In another word, this is a chain of elements, and there are, you see I'm using the symbol here, less than or equal, so that means this is strictly less than. Okay, and we come up with the chain of elements that are strictly less than to each other, nearby elements. You take the supremum of this thing, and that's finite. So this is the finite rank. Again, I'll talk about this thing a lot. And you want to think about this as a, so the first example you have is of a geometry is the one with the vector space and its subspaces. And I have shown that it's complemented, it's modular, and it's irreducible because the only irreducible. I showed that if you have a W that's not equal to the whole space or the null space, then it has more than one complements. So it's irreducible and modular and finite rank. Finite rank comes from, so you want to find the chain of proper subspaces inside the vector space, and you can show that if you have a chain, then you have a linearly independent set inside. If you have a chain, then you can pick a element from each subspace that's not in the previous one, and those would form a linearly independent set. So that means the length of a chain is less than or equal to the dimension of the vector space. So if you consider L of V, where V is finite dimensional, and that's an example of a geometry. Okay. And then we'll go through, we'll try to bring a lot of stuff into this. And we'll show that we'll work with the ideals in a ring or like an algebra. And then you'll show that those things form a geometry too. And then the finite rank condition, those we have to throw in like we did module theory, like Noetherian, Arterian conditions, like finite change conditions. Now you see, like now you have a place where both those things kind of merge. Because anyway, so vector spaces, subspaces, you have seen it in basis, and we'll do it in the case of algebraic geometry too. Okay? So, and then now let's move on. have to get a couple more definitions. Yeah. No, we have this guy, this thing. We're trying to get to the next big so this is a okay, so that's a geometry, and then you jump to the here. So let's go back here now. So the next definition is that of a Boolean algebra. So the Boolean algebra is a complemented distributive. That is called Boolean algebra. Okay, and see, like I have the distributive properties, and we call a lattice to be distributive if those conditions hold for all the elements. And the main theorem that you're going to prove is if you have a Boolean algebra in the lattice format, we can actually find a set and subset, a collection of subsets that form Boolean algebra. So that's the stone representation theorem. Okay, now finally, the last piece that we need is the definition of a logic. Okay, to get to that, we need this guy. So we had the difficulty in the case of subspaces of a vector space. We didn't have a unique complement, right? So, but if you have a inner product, you have a subspace, then you can find the orthogonal subspace to that. Okay, so in that case, we have kind of a special complement that's called orthogonal complement. Okay, now this is the formulation of that in the case of in the lattice language. Okay, let L be a lattice. Map. Let me denote it by this thing. Going from L to L, that sends, for example, we call this thing of A, we write it A perp, okay? Perpendicular. Satisfy. Following properties. Is called an auto-complementation. Okay, so the first property is this thing is a bijection. The second property, okay, they have a bigger element, and the auto-complementation is smaller. Part C, this is an involution. If you take the auto-complementation twice, then you land in the same space and same element, and their complements. Okay. Finally, we have this thing. This is the last definition. A lattice with an auto-complementation is called a logic if it satisfies these two conditions. It is sigma complete. That means you have the countable meets and countable joins. And if this is a strange property, but it's okay. If we have two elements, A1 and A2 in L, and A1 is less than A2, then there exists a B in L such that B is less than A1 complement, and B union A1 is A2. So this is basically telling you that you can take complements inside the element A2. Okay, so this is so this B is actually capital A2 minus A1 in the case of sets. Okay, and you think of the lattice of propositions, which you haven't gotten to yet. That then this B is this A2 proposition and not of A1. Okay, these are like two particular examples, and okay, and it is the what we call logic of a mechanical system. So in the case of classical mechanics, It is a Boolean algebra. And in the case of quantum mechanics, it is logic. So the main example for a logic is in a Hilbert space, the lattice of closed subspaces. We need the closeness because we don't have this type of things. When you define the complement, orthocomplement, that's always going to be a closed subspace. And if you take we apply this thing twice, you better land in the closure of A. Okay, so we'll go through all that. So somehow we'll define what a mechanical system is in using this language, and then the main theorem is main example is the closed subspaces of a Hilbert space, and then we will do a lot of stuff. We define basic quantities in there, and yeah, I mean, up until now, there's nothing happened. It's a whole bunch of words and trivial properties, okay? And we can define what a mechanical system and all the, like what observable and all that, kind of without doing any functional analysis. Okay, so that's kind of that's one thing I like about this part. And another reason I like, so let me get back into here. This is again for the people who give up on this thing. You can't blame them because I've been wasn't on top of things myself either. So we have posets here, partial ordered sets, and then we have here in this world, it's called space. And this word is algebra. Okay, so let me kind of tells you like what the next steps are. So we'll talk about limits and topologies, and there's something called null of a category. So those things are lives in here. Okay, and what you're going to do, you study, talk about those things, and then we relate them back into here. Okay, we move those concepts from then you define like the limits and all that, directed sets, and then you think of, we have the filters and all that. You kind of extract, you'll build a space out of it. Okay, and so that would be example of going from posets to, call it lattices. Everything that we talk about are going to be lattices, and it's okay. Directed sets are not lattices, but it's okay. You can kind of create the one that's generated by that subbase. That's a topology, so it's a lattice. Anyway, so let me keep the lattice view, and then we'll do something stone representation theorem. Okay, so the stone representation theorem, it's the example of a lattice that's a Boolean algebra. And again, we'll construct a space that's a it's going to be special type of topological space. Which is basically we'll add more kind of parts to what we did for the topic 1 limits topology and that thing. Okay, and then have a third topic. So fun thing. This is the fundamental theorem for coordinate geometry. Okay, so that this tells you again, we start with the lattice side, we start with that definition of a geometry, and we will show that given any geometry, we can find a vector space V, which is finite dimensional, where that those points in the lattice, they corresponds to lines and planes and so on. Okay, this is a huge theorem. Okay. So again, you're going from the lattice side to space. Okay, that's again you can think of as some representation theorem for geometry. Okay, and before let me call this thing 3. Before doing that, we will define the dimension of a geometry, which is a easier thing, and then we'll prove the one from the algebra side. Okay. So algebra side means you define the dimension of a algebraic variety. Those things happen with the Noetherian and Arthurian, like those conditions, chain conditions. Okay. So the dimension of geometry, and the main thing is we would be bringing an example from here. We call this thing 4 and this is 3. Defining the dimension in the lattice side is easy. Then we will talk about independent sets and bases and equal things in there. The fifth topic is the spectral theorem. Spectral theorem for matrices, linear algebra. Okay, and then you talk about so spectral theorem for linear algebra matrices. I mean, we're going to spend a lot, like the whole course is going to be about this. Okay, spectral theorem for like various kinds of operators. We will get to the unbounded operators, but we'll do the spectral theorem for matrices just at the beginning. For matrices. Okay, so that would be example where you go from here to here. You go from algebra to space. You start with the algebra, and then the 6 is going to be like that too, where instead of algebra we have a ring, and then this is important, and this is where we have the first appearance of the numbers. So the one that we do for matrices that has more structure, but with this schemes, starting with the ring, and then you look at the prime ideas, and so on. Okay, so the going back and forth is, if you have a space, you can construct an algebra by looking at the algebra of functions or algebra of I mean, if the space is some sort of topological space, and in that case you're dealing with the your space is your algebra is a space of continuous functions, and you're in the commutative setup, and that would be example for the numbers. Okay, and then in the space is vector space or a Hilbert space, and then you land in the non-commutative setup algebras. Okay, so you have the Boolean algebras. Let me put this thing in here too. So you have geometry. Okay, So in the geometry one, you land in a vector space, and then the Boolean algebra, you land in just a set or like topological space. It is commutative. Okay. Topic 7. So you'll talk about classical mechanical system. Okay, so in the classical mechanical system, what you really get to we already have the stone representation theorem. So you have Boolean algebra, you represent it with the uh, topological space, and then you can like define dynamics and everything. Those would be flows on that continuous or flows on that topological space. Okay, so we'll get to that, and then we have a quantum mechanical system, and this is the it's a very detailed. When you're going to spend a lot of time on this thing, you'll define what a mechanical system is in the lattice side, and you'll kind of recover the formulations that you see in like a beginning quantum mechanics course, where everything is operators. Okay, so the 8 would be something going from here. So 5, 6, 7 is also going into this arrow. So typically going from space to this is easy. Okay, and then 9. So this is something so the kind of the sad news is we have this space that we are like really familiar with, but this is gonna go away. Okay, so when you have this area, I don't know much about it, but I'm trying to kind of move these concepts that were in the space into the lattice side, and then you kind of build the intuition from there. And then the NCG ones, for example, in here they called measure space is a one-Newman algebra, and the topology is a C-star algebra, and so on. They have like a different dictionary, call it like non-commutative mathematics. But I'm trying to see if I can do this. Okay, so you take our intuitive ideas from space and you move it to the lattice side from the very beginning. Okay, so you make everybody comfortable with the lattice side, and then later on I'll drop the space. Okay, and then hopefully I'll get to a point where I can say like, yeah, of course this is the correct thing to, because in this space side you have already like what is the differential geometry, what is a measure, and this and that, what's a topology, and I'm bringing all these things one at a time to the lattice side, and then you build this red arrow 9. Okay, and in that way it's not a magic like when you have the NCG, you kind of have a big idea. And with this generalizes this is the non-commutative measure space, this is non-commutative topology, and this and that. Okay, but I'm trying to see if I can give some idea about this thing. I don't know much about these things anyways. Okay, but I would like to see it from that side. And ideally, like I would kind of give some motivation for the students who would ended up working in those areas. The 10 is again geometry, and this is like have the sheaves and everything. That thing is already in here, okay? So so when you have when you define geometries, like what you do, you have the open sets, and for open sets you attach additional structure. I mean, when I say geometry, this is the basic one. I want to kind of convince you that this is the good definition of a geometry. And then we have seen like algebraic geometry, differential geometry, this and that and that. I want to say that all those things are actually, we have the kind of the nerve of nerve of a covering. That's the lattice picture, and then you attach for each of those nodes to some other additional objects, and that's the definition of a sheaf. I mean, write it down properly, and I want to like bring that thing into here too. Okay, so this is kind of my plan, and the last thing is put it here. I'll do some. So in the algebras, I'd have numbers. I'm interested in the integers, and then you have. I'll talk about theta functions, and from here L functions, or like zeta, Riemann zeta, right? And I will do it from the trying to stay in the while staying in the same picture. Okay, so yeah, I think that's it, and this is kind of an invitation to kind of to keep following this thing, and I'm a little slow and posting the lectures and everything, but let's see, let's keep going. And this would be a now together with this, if you look at Piazza post on the syllabus of the course, yeah, I mean, the most of these things I'll do like at what I call the lecture 1, and the things that's gonna take us forever is basically coming up with proving various versions of spectral theorems, and then you have the Gleason's theorem. That's the main theorem that connects this lattice definition to the one that we know, and then this one. Okay, but now I have this picture with like 3 worlds, and we'll go from there. And yeah, I'll stop there and I'll upload this thing, and we'll see. Okay, stop recording.